So today we'll look at, we'll start working on techniques for solving first-order differential equations. And the first technique is the main one that's available just because you've taken calculus. That's integration. So in general, you cannot always do this because a first-order differential equation is going to be something like x prime equals and then a bunch of stuff involving x and t. So I could represent that like this. X prime equals a bunch of stuff involving x and t. So for example, x prime equals like x plus t. There's no way I can just use integration to solve this. You could say, let me write this more clearly. You could say, well, why not just integrate both sides with respect to t? Well, you could, and then on the left side you'd get x of t, maybe plus c or something like that, equals integral x of t dt plus 1/2 t squared, maybe plus c. But this doesn't help you. This does not get you anywhere. It's true that if x prime equals x plus t, then this stuff holds, but your goal when you're trying to solve a differential equation is to actually get x, right? And this gets us nowhere in terms of getting x. This gets us nowhere in terms of finding the function x of t. How are you going to solve this for x? You've got x here sitting by itself, and you've got x in an integral here. So actually all you've done, going from here to here, all you've done is just converted this differential equation into an integral equation, which is no easier to work with, actually. So it's just, you've just rewritten the differential equation in an equally complicated form, if not more complicated. Alright, so here I'm showing you when integration does not help you solve a differential equation. Now, when does it actually help you? So the trouble with this example was that there was some x dependence. The trouble is that when you're looking at a differential equation, it's going to be something involving x prime and t and also x. But what if that x dependence were not there? What if it were just some function of t? For example, what if it's x prime equals t squared plus 1, something like that? No x's, so I'm not adding x, and I'm not multiplying or dividing the whole thing by x. No x's get involved. In this situation, we can solve by integrating. So let's do that. Let me write it more carefully first. When I say x prime, I mean x prime of t equals t squared plus 1. And the goal, when I'm writing down a differential equation, the goal, or what we refer to as a solution, is a function x of t that satisfies it. So what does this differential equation demand of x of t? It demands that the derivative of x of t be t squared plus 1. So all I need to do to find a solution is find something whose derivative is t squared plus 1. Finding something whose derivative is a certain thing is called anti-differentiating, which you may have learned in calculus can be done by integrating. So what we're doing is integrating both sides. So another way you can think about this is, it's like when you're solving algebraic equations, like if you've got 3y equals 5, how would you solve this? You would divide both sides by 3, like that, and then get y equals 5/3. So when you're doing algebra, you do the same things. You do the same thing to both sides of an equation, so as to work towards isolating the unknown, so that you can solve for it, right? So you always just do the same thing to both sides of the equation. Here we're doing that as well, except the thing that we're doing to both sides of the equation is integrating in order to undo the differentiation, as opposed to dividing by 3 there to undo the multiplication by 3. Okay, so integrate both sides. Then here we get x of t equals, and then there we get 1/3 t cubed plus t. Now, this Okay, so this is what I have found here is one solution to the differential equation, and it is a solution. So if you were given this differential equation and you were asked find a solution to this differential equation, then you could give this and you would be correct. Usually, though, you're not being asked find a solution. You don't want one solution. You want to find all possible solutions. In other words, you want the general solution. This is not the general solution. And what I have forgotten here is that when I integrate, there's a plus c. So here I integrated and there's a plus c, and here I also integrated and there's a plus c, but it could be a different constant, so maybe plus d. Now, when you integrate both sides of an equality of functions, when you integrate both sides, you actually only need to add the arbitrary constant to one of the sides. You don't need to add it to both sides. And the reason for that is that you can just subtract it from one of the sides. So for example, I could subtract the plus c here, and then subtract it to this side. And if d is an arbitrary constant and c is an arbitrary constant, then d minus c is just an arbitrary constant, and I might as well give that a single name. So in order for x to solve the original differential equation, x of t should be this plus some number. And, why write the number in such a complicated way? I might as well just write it like this, and I'll just call it c. So here you have the general solution to the original differential equation, which was x prime equals t squared plus 1. Let's just briefly look at how you would solve an initial value problem. So here's an initial value problem, same differential equation, but now I've also given an initial condition. That should be sufficient to pick out one particular solution from my general solution. So we already had that the general solution was x of t equals 1/3 t cubed plus t plus some constant. And this parameter, since this could be any real number, this is actually an entire family of solutions, and that's why we call it the general solution. And then we impose the initial condition in order to find what value of c will make the initial condition hold. So we demand that the initial condition hold. So the initial condition says that 10 should be x of 3. And x of 3, depending on what I choose for c, x of 3 will be this. Will be that, right? So just putting in 3 for t. So in order for the initial condition to hold, what must c do? Well, it must be such that this equation holds. 10 equals this stuff. So this is an equation that I can solve for c. So let me simplify the equation a bit. This is 3 squared plus 3 plus c. So 1 equals 3 plus c. So minus 2 equals c. And so now I can write my particular solution. Let me go write it up here. So I have found that this is the solution. 1/3 t cubed plus t minus 2. Because this is the general solution, and I found that when c is minus 2, the initial condition is satisfied. So here's the, it seems unique, function that solves the initial value problem. Both satisfies the differential equation and satisfies the initial condition. So one thing I showed you last time with differential equations is that even if you haven't solved a differential equation, you could always plot a slope field for the differential equation, ignoring the initial condition, just the differential equation, and look at that slope field as a way of visualizing the entire general solution. So let's do that for this. Forget the initial value problem. So just go back to the general differential equation, and let's look at a slope field, what it looks like for this, and see if it shows this kind of behavior. Okay, here's our slope field, and as usual with slope fields, I'm only putting in the information of the differential equation, nothing about the solution. So all you see is basically like this info here. And you can see, if you try to create curves that follow these, they do look kind of like cubics, actually. So that's nice in that it's depicting this cubic solution that we got. And yeah, what else? So if you look at the way we generate the slope field is we look at this expression in front of x prime equals. We look at this expression, and then at each point in the tx plane, each point in this plane is a tx pair, and at each one of those points, this expression gives us a slope, right? And then we put a little line segment with that slope there. Well, if you look at this expression, it doesn't have any x's in it, right? That was the point, actually, is that's why we could use integration. So this expression does not have any x's in it. That means as we change x, as we move up and down, remember the vertical axis is x, as we move up and down, it doesn't change what the slope is. So that is nicely depicted here in the slope field. You see how along any vertical line, the slopes of the little segments are all the same, right? Along this whole vertical line here, the slopes are all the same. Along this whole vertical line, the slopes are all the same. And that kind of also nicely depicts what is the effect of this plus c in the general solution. The plus c is saying, look, if you have a solution, then you can vertically shift it, up or down, and that will also be a solution. That's what the plus c is saying, and that makes sense in the slope field, right? If the little segments look exactly the same as you move up and down, then you can vertically shift any solution, anything that's always tangent to the segments, and that will always look the same. That will always match up as you vertically shift it. Actually, let me plot a solution and show you. So here I've wrapped everything in a show, and I'm going to add a plot, and that should show both the slope field and the solution plot in the same picture. So my solution, that was 1/3 t cubed plus t plus c. So 1/3 t cubed plus t plus c. And let me choose 1 for c for now, and then I'll just put some other number there in a moment. And I'm going to plot that for t from -2 to 2. And I'm choosing those numbers because I happen to choose that my left and right bounds here, my t bounds, be -2 and 2. Okay, let's see if it works. Yep. So you see this line is my solution, and you can see that the solution, anytime it is about to touch a line segment, it looks like it would touch tangentially. So that's nice. And let me stick a c here. Now if I plot this, the solution has disappeared because it does not know what c is. However, I can create a nice manipulate bar and let c vary from -1 to 1, say. Then let's watch it play out. So as I move c, the solution graph moves up and down. Now, I feel like there's kind of an optical illusion or something where it looks like it's swishing to the side, but it is moving up and down. That's what's happening. This line here is moving up and down. And anytime it touches any of the line segments, it touches tangentially. So this is the general solution. Now, for situations where it's not like this, x prime equals something only involving t, for the more complicated first-order differential equations, where you could have a function of x and t here, it'll look different. You won't get this nice plus c, like you saw with the infection model from the previous lecture. The c showed up doing something else, not being added, but it was multiplied by the solution. And so we had something quite different from what's going on here, where it just moves up and down as I look through the family of solutions. Sometimes it does other things than move up and down. But in this situation, where you can solve by integrating, you get a plus c from the integration, and your solutions just move up and down as you look through the solutions in the family.